Hey guys, it's Mr. Nakmi here. Hopefully you guys are ready to do some calculations for area between two curves. We started this up the other day and I'd like to continue it. This is an example that we've done before, right? And I'm just hopefully that this will refresh your memory about it when we talked about it on Monday, right? To find the area between two curves is very simple, right? To get the area underneath of the curve that's on top and then just subtract it from the area that's on the curve that is on the bottom. So for example, here, the curve that is on top for the interval that we're looking for, which is going to be from 0 to 3, we find out that the function y is equal to 3x is the function that is on top, and that is going to be subtracted from the area from the function that is on bottom, which is y is equal to x squared, which is this blue line underneath, right? And we already knew how to calculate area. That was just simply us using the integral. We just had to find out where to where, and then evaluated that. And we were able to do this last time, right? Today I want to go over an example that's a little bit more difficult, which will be this one right here, example 2. We're going to find the area of the region bounded by the graphs y is equal to x cubed and y is equal to x to 4x, right? And if you look here, we have two regions here, right? We have one area that is bounded down here in the third quadrant. We have another area that's bounded up here. And I'm going to name these two regions. Let's see here. This one down here will be region A, and the region over here will be region B. Right? And we're going to be calculating those areas and summing them together. Okay? Now, why did I name them 1A and 1B? Well, if you look closely, right, region A, the function that is on top is your x cubed function. And then we look at region B, the function on top is the 4x function, you see? So if we integrated this and kept it the same all the way through from wherever we start, wherever this point is down here, and continued all the way up to this point up here, it would get messed up, right? It has to be the top function minus the bottom function, and at this point right here is where it switches, and if we don't take that into account, you're not going to get the right answer. Okay? So first things first, this has been graphed for us, and we can kind of see where these graphs are intersecting with each other, but if we didn't have this for us, we need to find that out algebraically, and that's simply just setting the two functions equal to each other, or using your graphing calculator to calculate that for you as well. Okay? In this case, let's just do it algebraically for those of you who need a little bit of a refresher of how to solve a cubic, right? So if I have the x cubed function equal to 4x, right, we can solve this. One strategy is to set it equal to 0. So I'm going to subtract the 4x over, and I'm going to have here x cubed minus 4x is equal to 0. Factor out a common factor. It looks like they both terms have a x in common. So I have x times x squared minus 4. And this is a difference of two squares. We can factor that again. So we end up with x times x plus 2 times x minus 2. That's equal to 0, right? That gives us 3 points of intersection. We have x is equal to 0, x is equal to negative 2, and x is equal to positive 2. Right? So that looks like it happens to be where they are crossing. So now I figured out what are my limits for my integrals are going to be. Right? That's the first part. Now let's actually do the calculus part, yeah? The fun part. Now, we're going to go ahead and look at the region A, which is going to be from negative 2 to 0. And that's going to be my integral limits there. It's going to be from negative 2 to 0. And then the function I'm going to have inside here, this is important, you understand which function is on top and which one is on bottom. The function that is on top in this case is going to be x cubed. So that's going to go first. It's going to be x cubed minus 4x. See here? Minus 4x. That's because this function is the one that's on top minus the function that's on bottom. This will help me calculate the area between those two curves, right? That's for this guy right here. And that will give me that area. To find the next part, region B, write this out first. This is the area for region A. And then for the next part, we're going to have here, for region B, it's going to go from 0 to 2, right? That's what we calculated, that it's bounded from 0 to 2. So that's what my limits will be for my integral, which will be from 0 to 2, okay? And on here, it's going to be 4x minus x cubed. You see how the functions have switched with each other. The function on top now is no longer x cubed. It's the blue line, which is the 4x function. Okay? And we have to switch that to take that into account, or else it's going to reverse it and we'll end up with a negative area. Right? And I don't know what that entails in this case for between two curves. Right? So we have here 4x, which is going to be our top function, and our x cubed now has become our bottom function. Okay? Once we figured out how to set it up, after that, now it just becomes a simple integral problem, right? Evaluate it, take the antiderivative, and, well, the other way around, take the antiderivative and evaluate it at those endpoints. All right, so we have here the integral of x cubed. This is going to come out to be, using the power rule, x to the, I don't like that, hold on a second. It's going to be x to the 4th over 4 minus the integral of, the antiderivative of 4x, I believe, is 2x squared, right? We can double check that by taking the derivative. Power rule, yes, it comes back to 4x. This is going to be evaluated, of course, from -2 to 0, plus this integral over here, which is going to be pretty much the same thing, isn't it? It's going to be now 2x squared minus x to the 4th over 4, but this one is evaluated from 0 to 2. I should do a good job, and I should do a better job, I should say, and separate these guys with more symbols of inclusion. There we go. And then we go here and just evaluate the 2. We just start plugging it in. So over here, when I plug in 0, I am going to get 0 to the 4th over 0 minus 2 times 0 squared. I believe that's just 0. Minus, plug in the -2 this time. This will be -2 to the 4th over 4 minus 2 times -2 squared. Okay? Whatever that is. Plus, and we'll do the same evaluation along the way over here, and we get over here, this is going to be plugged in with a 2, so I get 2 times 2 squared, that's from this 2 right here, minus 2 to the 4th all over 4, right? But this, of course, is being subtracted with the same function being evaluated at 0, which would be 2 times 0. I'm not even going to write that out. 2 times 0 squared, which is 0, minus 0 to the 4th over 0. That's just 0 still, right? And let's see here. Let's scroll this down a little bit here. Let's do some algebra now. This is the part where I got to be careful, right? The algebra is the part that we tend to make our most mistakes on. Over here we get 0 minus -2 to the 4th, I believe, is 16. 16 divided by 4 is just 4, right? Minus -2 squared is going to give me +4. +4 times -2 is going to give me -8, okay? That's that part right there. We're going to keep going over here. Same calculation, just different signs over here. 2 times 2 squared is going to give me 8 minus 2 to the 4th over 4. That's still going to be a 4. And of course, this is also subtracting with 0. Okay? On the left-hand side over here, I'm going to have a -4, which is going to come out to be a +4, plus 4. So the area that is pinched between those two curves, between A and B combined, is going to be an area of 8 units squared, right? 8 units squared. And that's how we calculate the area between two curves. It's quite a bit of work, but the calculus setup is fairly short. It's just understanding how to set it up, yeah? We need to make sure that we understand that when we do the integral from beginning to end, we take into account which function is on top and which function is on bottom. And if there is a point where they switch, we actually have to break it up into two integrals now instead of just doing it all the way through like we did in the previous example. See? I'm going to go ahead and give you a second there. I'm going to move on to this next one. This next example right here, example number 3. I'm looking for the area of the region bounded by the graphs. This time it's not a function of y equals x. It's now x is equal to y squared, right? Which puts our graph sideways here. And x is equal to 10. So I'm looking for this region here. Well, how am I going to do this? Well, I got a couple options here, but I'm going to show you the main way. Not the main, I shouldn't say that. The easier way for this particular problem. It's not easy for all problems, but it'll be easier for this particular problem. Okay. Now we have this equation right here. X is equal to y squared. Yes? And I don't like that. I want to do this in terms of x's since I've been doing my integrals with respect to x. Yeah? So I could just solve this for y, and simply by taking the square root of both sides, right? And when I take the square root of both sides, I end up with y is equal to plus or minus the square root of x. Please make sure you understand that, right? When we do that square root of a variable, you got to include that plus or minus. If you only have the square root of x, you're only going to have the top part of this graph, which you can clearly see would only give you this half of the area, right? That's for y is equal to the square root of x. Now, if we take a look at the negative part, that's the bottom half down here. This is where y is equal to negative square root of x. See, we're splitting that up into two separate functions because we need to make sure we include the top and the bottom for this one. Okay? In this case, x equaling to 10 seems to be just our limiter. It's basically telling us where we are going to start from, which is going to be x equals 0, and it works our way out to here, which is going to be x equals to 10. And it looks like that for both sides, right? Which doesn't matter because it's going this way anyways. We're working our way from left to right. Okay? So we're going to go ahead and do this and calculate the area between those two curves. And again, it should be pretty straightforward. We're going to go ahead and just do the integral. And this time it's from 0 to 10. We did not have to do any algebra to calculate where those things intersect, but it wouldn't be too hard to do so, right? We could just plug it in and see. Now the top function in this case, I'm going to split this up just so we can see this a little bit better. Okay, I'm going to write the top function as y is equal to the square root of x, and the bottom function as y is equal to negative square root of x. Okay, so you can see that we're doing this one up here minus this one down here to get us the area that is between the two. Okay, so the top function is going to be the square root of x minus the bottom function, which is going to be negative square root of x. Okay? Let's make that color-coded so we can see that a little bit better here. This is the top function, right? And this one over here, right? That's our bottom function. Okay? This of course, is all with respect to x, because that's what we've been dealing with for our integrals. All right? Let's simplify this out a little bit. This is going to become the integral from 0 to 10 of x to the 1/2. Negative and a negative becomes a plus x to the 1/2 as well, dx. Okay, let me see here. Scroll that down a little bit. This is going to become the integral from 0 to 10 of 2x to the 1/2. Since they're like terms, I can combine them, dx. And I'm going to go ahead and integrate from here. So the integral of 2, and I have over here, this is going to be x to the 3/2 using the power rule, and then the coefficient in front will be that the reciprocal of that power, which is going to be 2 over 3. This, of course, is being evaluated from 0 to 10, right? Now we'll go ahead and do that, and we'll end up with, let's see here, this is going to be equal to 4 over 3 times 10 to the 3/2 minus 4 over 3 times 0 to the 3/2, and that's just going to be 0. Okay? And when this is worked out, we end up with, let's see here, give me a little bit more space. Whoops. This will be equal to, let's see, 10 to the 3/2 is going to come out to be, it looks like the square root of 1,000. And if we simplify that, that is 10 times 100, and that is 10 times 10. So it looks like 10 to the 3/2 is going to come out to be as 10 times the square root of 10 multiplied with 4 over 3. So if we simplify this completely, this is going to come out to be 40 times the square root of 10 all over 3 units squared for this area here. Now, what we could have done, and some of you might have already noticed on the previous example, is that if we see things that are symmetric, we technically don't have to do, this is like twice the work. If I saw that this was symmetric, I can see that I could just calculate the area over here and then just double it. See that? And I can get both of them combined. If you look over here, I pretty much have the same thing happening here, right? This area, let's call this area A, and this one down here area B, right? if I split them up, I would notice that it's symmetric around the x-axis. And I could technically just do the integral of the top function, right? If I do the integral of the top function, that would technically give me half of the area. And all I really need to do then is just double that, right? And I'm willing to bet if you were to do that integral, and I suggest you do it, practice the integral from 0 to 10 of just the square root of x. And I'm thinking that you should end up with 20 square root of 10 over 3. Yeah, you should go ahead and try that and see how that works for you. The third way of doing this, right, and I'm not going to do it yet, but there is a third way of doing this. You notice that I was doing this with respect to x, right, on this graph of an xy plane. Another way that you could do this is with respect to y, right? Now, with respect to y, instead of you working your way from 0 to 10, right, and then cutting your pieces vertically along the way, right, to do these areas underneath, you would instead switch this up and go from bottom to top. You would go this way with respect to y, and then you would cut your slices this way. See that? And the height of your function would now be in a function of x equaling your y stuff, and the top function would be x equals to 10, and your bottom function would be y squared in this case, to tell you that. And that actually just makes this problem a little bit more difficult in this case, but you could do it that way, right? And you're like, Nakami, what are you talking about here? And I'll show you in a second. We'll do another example with the respect to x problem, and I'll show you how it would be easier if we did it with respect to y, okay? All right, let's go down here. This is the next example I wanted to show you right here. Example number 4. Find the area of the region bounded by the graphs y is equal to the square root of x, y is equal to x minus 2, and y is equal to 0. Okay? Now take a look here. Y is equal to 0 is this line that's going horizontally across the x-axis right there, right? So the area that is bounded is clearly right here, right? This area right here. Boom. Yeah? Now, I can't integrate from 0 to wherever this is of the green function minus, well, the green function, what am I calling the green function? That's the square root function, right? The square root of x function, and I can't just subtract that from y is equal to x minus 2 function, because what will happen is if I do that from 0 to wherever, I'm not only just going to get the area that I've just shaded, but I'll also get the area that's down here because it's top minus bottom function, okay? And that's going to overshoot for me. So what I need to do is actually, I have to separate this function, this graph as well, into 2 regions and calculate those areas separately, right? So the first thing I need to do is see from where to where am I only looking at the area underneath the square root function. And that's clearly going to be from here to x equals 2, which is this cutoff right there. See? So I would do the integral from 0 to 2 of just the square root of x dx. When I do that, right, this right here gives me the region, let's call this region A, right? I've cut this up, right? And then region B over here would be a little bit different. I would then continue my integral, adding it to this one, which would be from 2 to wherever the heck this is, and it looks like it's crossing at 4 based off of this graph. Of course, you know, again, if you don't have that graph, you do this algebraically or use your calculator to help you figure that out. But see, for this one, it's still, you'll still see it. It's still the square root of x, right? It's still that function because that function is still up here. It's still the one on top. But I'm not doing it all the way down to the x-axis now, right? Now I'm dealing with this graph right here that's in the way. And that graph right there is x minus 2. And that needs to be included. I'm subtracting this entire function, x minus 2. Notice, though, by the way, I'm putting that whole thing in parentheses. I'm not just subtracting the x, but I'm also subtracting the negative 2 that's with it, okay? This whole thing is with dx. And you'll say, you know, this isn't too bad, and I agree, this isn't too bad in this particular example, but if I did it another way, which you do have other options, it won't be as much of a hassle. But let's just finish this one up here first. This, of course, is the region of B. So let's go ahead and calculate this integral just to see what this area is going to come out to be here. The integral from 0 to 2, this one right here is x to the 1/2. If I do the integral with the power rule, this is going to become x to the 3/2, right? Times 2 over 3. Right, this will be evaluated from 0 to 2. Plus, now this is one we need to break up. I should simplify this first. This should be x to the 1/2 minus x plus 2. Right, so we'll break this up and do the integral here. This will be, again, 2 over 3 times x to the 3/2 for that first term, minus x squared over 2 plus 2x, and this is being evaluated from 2 to 4. Okay? This is being evaluated from 2 to 4. I think my video is running a little bit long, so I'm just going to let you guys do the calculations for that. If you plugged in 2 minus 0 over here, it'll look something like this. It'll be 2 over 3 times 2 to the 3/2 minus 0, whatever that is, plus over here, that's going to be a mess. You're going to plug that all into. And when you do the calculations, it should come out to be 10 over 3. Right? I'll leave that up to you to check out if that is correct or not. Okay? Let me know if I messed up somewhere. But what I wanted to show you is the second way of doing this exact problem, and that is instead of doing it this way, which is this is the integral with respect to x. Okay? The thing I wanted to show you next was with respect to y. Okay? Let's see here. Where's my mouse? There you are. So I'm going to go ahead and move this graph. I'm going to go over to the side over here. And we're going to look at the same functions, but this time with respect to y. Okay? Now if I'm looking at this with respect to y, it'll be a little bit easier. Okay? I don't have to cut it up into two regions. Right? If I look at it with respect to y, that means I'm going, instead of going this way, right, from x equals 0 to x equals 4, and cutting it along the way right here at x equals 2, right, what I could do instead, right, is do it with respect to y and go this way, go from here up to that function, right, where this will be my top function and this will be my bottom function. Whoops. What I'm essentially doing is rotating this graph, right? That's all I'm essentially doing. Is just taking this graph and I'm kind of rotating it so that it ends up being integrated from right to left, from negative y values to positive y values. Okay? So in this case, instead of doing it from at this point, which is 0, 0, to this point, which is 4, 2, right? We did the integral from 0 to 4 when we did it with respect to x. With respect to y, instead, we can just do the integral from 0 to 2, working from down here all the way up to here. And the reason why this is simpler, or easier I should say, is I'm not switching up my integrals. It's going to be a straightforward top minus bottom like I've been doing before, and I don't need to stop my integral in between. I don't need to stop at 1 or 1.5 because, oh, the function doesn't have anything below it, or that function doesn't get enclosed by another function. Okay? And the way we do this is we just switch these equations to their equations where instead of it's y is equal to something, we write it as x is equal to in terms of y. Okay? And what does that essentially mean? That means this line right here, y is equal to x minus 2, that simply becomes x is equal to y plus 2. I'm solving it for x now, and this is an equation in terms of y, right? And the other function, which is y is equal to the square root of x, we can rewrite that as x is equal to y squared. See that? And x is equal to y squared would be our bottom function. If you tilt your head to the right and look at this graph sideways, right? X is equal to y squared is your bottom function, whereas x is equal to y plus 2, and with your head still tilted to the right, 90 degrees, you can still see that this black line is now the line that's on top, okay? And if we do it this way, right, it's still an integral problem. We're still looking for the area underneath the curve, underneath being this way now. Right? The top function now is y plus 2, whereas the bottom function, which we'll be subtracting, is going to be y squared. Okay? And that's it. That's how we would set up this integral, right? You don't have to do it this way. You can do it with respect to x. This is going to take you a little bit more time, and you have to find out what the intervals need to be, right? But I'm just letting you know, once you've mastered that and you have these other graphs that you're looking at, you might want to consider doing it in oh, wait. Oh, that's a bad mistake. It's not with respect to x, silly me. It's with respect to y. dy should be there instead. But if you notice, I don't have to do any complex integrals, right? And you'll see these on your homework problems and test problems. They'll get a little bit more funky. And if you're comfortable with this, you'll be able to do it with a little bit more ease, right? Because when we do this problem, this just becomes, what's the integral of y? That's going to be y squared over 2 plus 2y minus y cubed over 3. And this, of course, is just evaluated from 0 to 2. Doesn't that look a little bit easier to evaluate? I think it does. So let's go ahead and just plug that in here. We're going to go and plug in 2. We get 2 squared over 2 plus 2 times 2 minus 2 cubed over 3, right? This, of course, is going to be evaluated again when we plug in 0, but plug in 0 to all those y's is going to be minus 0. So over here we have, let's see here, 2 squared is 4, divided by 2 is still 2, plus 4 minus 8 over 3, right? So this is going to be, what is this, 6 minus 8 over 3. Common denominator would be 3, so this would be 18 over 3 minus 8 over 3, which gives us 10 over 3. Hey, look at that. It's the answer that I told you it should be if you worked it the other way, but with way, way much less algebra involved in this case, right? So hopefully this was helpful for you, and hopefully you guys will give this problem a try before you call it a day, of course. I'm not just going to let you go through that. If you get a second here, maybe you want to write down these steps. I'm not going to read it to you because there's a video. You can just pause it. I'm going to go ahead and scroll down, and I'm going to leave you with this problem right here that you should try. And I've already set up the Canvas page, so after you watch this video, tell me what you get as your answer. Work it out on a sheet of paper, plug it in to see if you're right. To get full credit, though, for this, I also need the work done submitted onto Canvas as well. So please, oh, there's a typo here. Find the area of the region enclosed by the graphs. And please take a picture of your work, whether it be done on a whiteboard or on paper, and submit that into question 2. All right. I hope you guys are doing well. I really miss you guys. Hopefully this will all blow over soon. I'll see you back in the classroom, okay? Have a good rest of your day.